Welcome to another episode. Before we begin, I'd love to know where you're listening from and what time it is there. Drop a comment below and share your little corner of the world. And if you enjoy drifting through science and thought as the fire crackles and the night slows down, remember to subscribe. It helps this quiet community grow. Tonight, we'll follow one of the strangest mysteries in existence. A mystery so familiar we rarely notice it, yet so deep that all of physics bends around it. It's the direction of time. We live inside its current, carried from past to future, from youth to age, from creation to decay. But why does it move that way? Why do we remember the past, but never the future? The equations that govern the universe, from Newton to Einstein to Schrödinger, don't seem to care which way time flows. And yet, everything we touch, build, or become slowly fades, breaks, and unravels. So tonight, let's drift into that mystery, into the story of time's arrow and the quiet law that gives it meaning. Entropy. Time has a direction. It's one of those truths so deeply woven into our daily experience that we rarely question it. You wake up, you age, you remember what happened yesterday, but not tomorrow. A cup of coffee cools down, but never heats itself. The stars that once formed from gas clouds will someday burn out. Everything, from galaxies to teacups, seems to obey this grand one-way rule. But when physicists look beneath the surface, that rule becomes suspiciously hard to find. If you could zoom down to the level of atoms, you'd see a world that doesn't seem to care which way time is flowing. The collisions of particles, the vibrations of molecules, they all look perfectly the same whether you play them forward or backward. The laws that describe them, the grand equations of physics, are time-symmetric. Newton's laws, Maxwell's equations for electromagnetism, even the delicate wave functions of quantum mechanics, all of them work equally well in reverse. And yet, here we are, prisoners of a forward-flowing world. So where does this arrow come from? This question haunted scientists and philosophers for centuries. The ancient Greeks had already sensed that time was not just motion, but change. Aristotle saw time as a measure of change, a way to count before and after. For him, time was tied to the movement of celestial bodies, the sun crossing the sky, the moon waxing and waning, the rhythm of nature. Time existed because things happened. St. Augustine, writing over 1,000 years later, found the mystery even deeper. In his Confessions, he asked, "What then is time? If no one asks me, I know. If I wish to explain it to him who asks, I do not know." Augustine realized that time was also a matter of perception, something experienced from within. The past existed as memory, the future as expectation, and the present as the ever-slipping point between them. Still, both thinkers, Aristotle and Augustine, saw time as fundamentally human, but physics eventually pulled time out of our minds and into the world. In the 17th century, Isaac Newton introduced a new idea, absolute time. He imagined time as a kind of invisible stage on which all of nature's events took place. It ticked steadily, identically, everywhere, an unchanging rhythm that made motion and causality measurable. In Newton's view, time was an independent river, flowing evenly no matter who was watching. Then came the 19th century, the age of industry and steam, of pistons, boilers, and the first real confrontation with the physics of heat. Engineers were desperate to understand why some machines wasted energy. They noticed that heat always flowed from hot to cold, never the reverse. A cup of tea cools on a desk, but the air in the room never spontaneously gathers warmth to reheat it. Out of this very practical concern, how to make engines efficient, emerged one of the most profound ideas in science, entropy. In 1824, a young French engineer named Sadi Carnot wrote a paper about the motive power of fire. He wondered how much useful work a steam engine could ever extract from heat. His analysis was elegant and visionary, though he died of cholera at just 36, never knowing he had laid the foundation for thermodynamics. A few decades later, the German physicist Rudolf Clausius gave Carnot's intuition mathematical form. In 1865, he coined the word entropy from the Greek entropein, meaning to transform. He declared that while the energy of the universe remains constant, its entropy, its tendency toward disorder, always increases. This was more than an engineering insight. It was a law that whispered something about time itself. Heat doesn't flow backward, things don't unmix. You can shatter a glass in a second, but not unshatter it in 1,000 years. Suddenly, physics had discovered a true arrow, the thermodynamic arrow of time. But even this law, when examined under a microscope, raises strange questions. If you could watch every atom in that cooling cup of tea, you'd see nothing illegal about running the film backward. Each collision, each vibration, would obey the same physics in reverse. The only difference lies in the overwhelming probability of certain outcomes over others. That was Ludwig Boltzmann's revolutionary insight. Entropy, he realized, wasn't about disorder in a moral or aesthetic sense. It was about statistics. Imagine a box full of gas molecules. At first, all of them might be squeezed into one corner. Over time, they spread out evenly through the box. Why? Because there are far more possible ways for the gas to be evenly distributed than for it to be confined. It's not that the molecules choose disorder, it's just vastly more likely. So, the arrow of time emerges from probability itself. Boltzmann even wrote his famous formula on his tombstone, S equals K times the logarithm of W. It's a reminder that behind every cup of tea and every fading star lies an ocean of microscopic chance. Still, probability alone doesn't fully explain why time feels one-sided. If the laws of nature are reversible, then why did the universe start in such an improbably low entropy state to begin with? Why not begin already in chaos, where nothing much changes? That question, known as the past hypothesis, remains one of the deepest puzzles in physics. But long before cosmologists took it on, Boltzmann himself wrestled with the implications. He proposed a strange idea. Maybe our universe is just a rare fluctuation within an eternally existing chaos, a low-entropy bubble where order briefly emerges. In that case, the very fact that we're here thinking about time might be a statistical illusion, a product of improbability. It's a haunting thought that memory, history, and progress could all be temporary ripples in a cosmic ocean of disorder. Yet for most of us, time feels anything but statistical. It's emotional. We feel it in aging faces, in the melting of snow, in the fading warmth of a hand once held. Entropy might be the physical explanation, but the human mind turns it into story, nostalgia, and meaning. That's what makes the arrow of time so fascinating. It's not just a scientific fact, but a bridge between the laws of physics and the way consciousness experiences the world. Even Einstein, who unified time and space into a single fabric, couldn't undo its pull. His equations showed that time can stretch, twist, and slow down under gravity, but they didn't say why it moves forward. Einstein himself called the distinction between past, present, and future a stubbornly persistent illusion. Yet even he could not live outside that illusion. None of us can. If we take a step back, entropy seems almost poetic. It is the quiet accountant of reality, keeping track of every spread, every diffusion, every transformation that cannot be undone. It tells us that the smoke from a candle won't unburn, that spilled milk won't reassemble, that order requires effort. It's easy to think of entropy as destruction, as the slow ruin of the universe, but that's not quite right. Without entropy, there would be no time, no motion, no life. Change itself requires imbalance. A world of perfect order would be a frozen, timeless stillness. the very absence of existence. So when your tea cools, or your memories fade, or stars die, that's not just decay. It's the ongoing story of transformation. Entropy is what allows stories to exist in the first place. And maybe that's what the arrow of time truly is. The universe's way of telling its story, one irreversible moment at a time. Next, we'll explore where that story began, in the roaring furnaces of steam engines and the equations that gave birth to the very concept of entropy itself. But for now, take a breath. Look around your room, the stillness of the present, the traces of the past folded quietly into every atom. Time's river continues, and we, tiny observers, simply float within its current. The 19th century was an age of fire. Steam curled from factory chimneys, black smoke smudged the skies of London and Manchester, and the hiss of pistons became the rhythm of progress. The Industrial Revolution wasn't just a transformation of society, it was a transformation of energy. Humanity had learned to burn ancient sunlight, locked in coal, and turn it into motion. But behind the roar of engines and the glitter of railways, a quiet puzzle smoldered in the minds of scientists. Why did some machines waste so much heat? Why couldn't all the energy of burning coal be turned into useful work? The answers to those questions would lead not only to better engines, but to a deeper understanding of the universe itself and the first hints of time's arrow. At the heart of this story stands a young Frenchman named Sadi Carnot. Born in 1796, Carnot grew up during an age obsessed with power, political, industrial, and mechanical. France was building steamships, England was building locomotives, and both nations were racing to harness the strange new force that seemed to animate the modern world: heat. In 1824, at just 28 years old, Carnot published a book titled Reflections on the Motive Power of Fire. The title sounds poetic, and it was. Carnot saw fire as a kind of spirit-animating matter, a universal source of motion. But he also had a meticulous engineer's mind. He asked a simple, revolutionary question: what is the most efficient possible engine that can turn heat into work? To answer it, Carnot imagined an idealized machine, a perfect engine that operated between two temperatures, a hot source and a cold sink. Heat would flow from the hot reservoir to the cold one, and in the process, the engine would extract work. But even in his ideal case, Carnot realized that no engine could ever be 100% efficient. Some heat always had to be released to the cold side. It wasn't a flaw of design, it was a law of nature. Carnot didn't yet know about atoms or energy conservation. Those ideas were still decades away. But his insight was astonishing. Efficiency depended not on the material of the engine, but solely on the temperatures between which it operated. The greater the difference between hot and cold, the more work you could get. But total conversion was impossible. Carnot's conclusion seemed merely practical at the time, yet hidden within it was the seed of the second law of thermodynamics, the principle that would define the irreversible nature of reality. Sadly, Carnot never saw how profound his ideas would become. He died young, at 36, of cholera in Paris. His notebooks were burned during a sanitation panic, and only his slim 1824 volume survived. But that little book would ignite the science of heat. A generation later, in Germany, another mind picked up the flame. Rudolf Clausius, born in 1822, was a physicist who sought to formalize what Carnot had begun. By Clausius's time, scientists had begun to understand that heat was not a mysterious fluid, as once thought, but a form of motion, the jostling of countless invisible particles. Energy, they realized, could change forms, from heat to motion to light, but it could never be destroyed. Clausius expressed this new understanding in 1850 with a simple statement: The energy of the universe is constant. Then, 15 years later, he added the line that would change everything. The entropy of the universe tends to a maximum. With that, he gave birth to entropy, a new quantity, as fundamental as energy itself. Clausius invented the word from the Greek en within and tropein, to transform. Entropy measured not energy itself, but how spread out or unavailable that energy had become. When heat flows from a hot object to a cold one, the total energy doesn't vanish, but it becomes harder to use. The system's entropy increases. In simple terms, energy can't be destroyed, but it can be degraded. Once it's spread out evenly, it's no longer capable of doing work. You can feel this principle everywhere: the warmth of a fire radiating into a cold room, the smell of perfume diffusing through air, a drop of ink dispersing in water. In each case, order dissolves into evenness, gradients flatten, and possibilities fade. That's entropy, the great equalizer. And with it came a shocking realization: nature has a preferred direction. Carnot had hinted at it, Clausius named it, and soon another physicist would explain it. In the late 1800s, Ludwig Boltzmann, brilliant, eccentric, and endlessly curious, sought to understand why entropy always increases. Clausius had described the what. Boltzmann wanted the why. Boltzmann's genius was to think statistically. He realized that the laws of mechanics didn't forbid any particular arrangement of atoms, but some arrangements were simply far more likely than others. Imagine, he said, a box filled with gas molecules. At one moment, they might all be bouncing around chaotically. At another, they might accidentally clump into one corner. Both arrangements obey the same physical laws. The difference is in probability. There are vastly more ways for the gas to be evenly spread out than for it to be clustered. So, over time, it naturally evolves toward the more probable state, toward disorder. Entropy, Boltzmann concluded, measures the number of possible microscopic arrangements that correspond to the same macroscopic appearance. He expressed it in a formula that would outlive him: S equals K times the logarithm of W. Here, S stands for entropy, K is Boltzmann's constant, and W is the number of microscopic configurations, the ways the system can be arranged. To Boltzmann, the arrow of time emerged from simple arithmetic. It's just overwhelmingly likely that systems move from less probable states to more probable ones. A freshly stacked deck of cards, ordered, has one possible arrangement. A shuffled one, disordered, has billions. Once shuffled, the odds of it spontaneously returning to order are astronomically low. That's the heart of entropy, not chaos in the dramatic sense, but probability itself. Boltzmann's insight united the mechanical and the macroscopic worlds. It explained why microscopic reversibility gives rise to macroscopic irreversibility. The atoms follow time-symmetric laws, but the sheer number of them, trillions upon trillions, makes reversals practically impossible. From that realization, the arrow of time was no longer a mystery of divine decree or cosmic rhythm. It was the natural consequence of statistics. But this also raised unsettling questions. If entropy increases because high entropy states are simply more probable, then why did the universe begin in such a low entropy state? That initial condition seems outrageously unlikely, almost suspiciously so. Boltzmann pondered this too, proposing that maybe our entire universe is just a rare fluctuation within an infinite, timeless sea of equilibrium, a brief, ordered bubble amid endless randomness. It's an eerie idea, and one that haunted him. In such a universe, consciousness, memory, and history might themselves be statistical accidents, fleeting mirages formed by chance. Few accepted the idea, but it showed how far Boltzmann was willing to chase the implications of entropy. He even imagined the Boltzmann brain, a single self-aware mind spontaneously forming in a high-entropy universe. The odds are absurdly tiny, but not zero. Still, Boltzmann's statistical view became the foundation of modern physics. Entropy was no longer just a thermodynamic curiosity. It was a window into the nature of reality itself. Unfortunately, his contemporaries didn't always see it that way. Many physicists of his time dismissed his statistical explanations as philosophical speculation. Others, like Ernst Mach, criticized his belief in the reality of atoms, which at the time had not yet been directly observed. The strain of being misunderstood weighed heavily on him. In 1906, while on holiday in Italy, Boltzmann took his own life. Just months later, experimental evidence for atoms, Brownian motion, explained by Einstein, would vindicate his entire theory. Today, his formula is carved on his tombstone in Vienna. It's more than a tribute. It's a summary of how the universe works. When you watch an ice cube melt, you're witnessing Boltzmann's law at play. The ordered lattice of frozen water molecules breaks into countless disordered arrangements as they melt. Energy is conserved, but the number of microscopic possibilities explodes. The system's entropy increases. That increase is the price of change, the measure of time's passing. Entropy doesn't mean that everything falls apart instantly. It's more subtle. Systems can maintain or even build order by exporting disorder elsewhere. That's how life works. It's a local reversal made possible by a global increase. When a seed becomes a tree, it decreases its internal entropy, but only by increasing the entropy of its surroundings. The same sunlight that powers its growth releases waste heat to space. So, entropy doesn't forbid complexity. It requires it. Without gradients, without flows from hot to cold, nothing could ever happen. Entropy is the quiet motor behind motion, the reason the universe doesn't sit still. That's the irony. Entropy, often seen as a force of decay, is also what drives everything that ever changes. Every spark, every thought, every heartbeat is a tiny rebellion against equilibrium, one that leaves the universe slightly more disordered than before. The physicist Arthur Eddington, in 1927, summarized it perfectly. If your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. Entropy is unavoidable. It's the one law that gives time its bite. And yet, it's not a villain. It's the quiet storyteller of existence, the invisible narrator marking each irreversible page. From the coal-fired engines of the Industrial Revolution to the ticking of your wristwatch, from the cooling of stars to the flutter of thought in a human brain, every process in the universe is a chapter written by entropy's hand. And with each word written, the arrow of time extends, a single, continuous line tracing the improbable journey from order to disorder, from creation to transformation. In the next part of our story, we'll travel deeper into Boltzmann's world, into the statistical dance of particles and probabilities, to see how entropy shaped not only the universe, but the very possibility of life and memory. For now, imagine the quiet hum of an engine, the whisper of steam, and the slow cooling of iron. That's not just machinery at work. It's time itself, turning its wheel. When Ludwig Boltzmann looked at the world, he saw it not as a collection of objects, but as a vast cloud of possibilities. Every gas, every grain of dust, every drop of water. He imagined them as armies of microscopic particles, each in ceaseless motion, colliding, rebounding, vibrating. The trick, he realized, was not to describe what every particle was doing. That was impossible, but to describe what most of them were doing on average. That shift, from the deterministic to the statistical, changed everything. It was a radical way of thinking about reality itself. To understand Boltzmann's vision, Picture a simple example: a box filled with gas molecules. We might describe it in two very different ways. The first is the microstate, the complete description of the position and velocity of every single molecule. It's the ultimate zoom-in, a map of everything happening in the tiniest detail. The second is the macrostate, the broad average description: pressure, temperature, volume. It's the picture we actually observe. The connection between the two is where the magic lies. Each macrostate corresponds to an enormous number of possible microstates. For instance, a room full of evenly spread air can be realized in trillions upon trillions of ways, with each molecule bouncing around differently. A room with all the air molecules squeezed into one corner, on the other hand, has far fewer microstates that match that description. The second is technically possible, but extraordinarily unlikely. If the air in your room suddenly rushed into one corner, leaving you gasping in vacuum, the laws of physics wouldn't forbid it. But the odds are so minuscule, 1 chance in 10 to the power of something like 10 to the 25th power, that you could wait longer than the age of the universe and never see it happen. That's entropy, statistically speaking, a measure of how many ways a system can be arranged without changing what it looks like from the outside. More microstates means higher entropy, and the reason entropy tends to increase is that there are simply more high-entropy microstates than low-entropy ones. The philosopher might say the universe prefers disorder. Boltzmann would have said it prefers probability. This view led him to formulate one of the most daring ideas in physics, the H theorem. It was his mathematical attempt to prove that, for a gas left to itself, a certain quantity, which he called H, would always decrease over time, signifying an increase in entropy. It was the first time anyone had tried to connect the microscopic reversibility of mechanics with the macroscopic irreversibility of thermodynamics. In essence, Boltzmann claimed he could derive the arrow of time from the billiard ball collisions of atoms, but not everyone was convinced. The H theorem sparked fierce debate among physicists and philosophers. Two of his critics, Joseph Loschmidt and Ernst Zermelo, posed what became known as the reversibility paradox and the recurrence paradox. Loschmidt's objection was sharp. If the laws of motion are reversible, then for any process that increases entropy, there must be another possible set of initial conditions that would make entropy decrease. If you could reverse every velocity, make every atom move backward, the gas would unmix, the T would unsteep, and time would appear to run in reverse. Zermelo's argument came later, based on the mathematician Henri Poincaré's theorem of recurrence. Poincaré had shown that in a finite, isolated system, if you wait long enough, the system will, with near certainty, return arbitrarily close to its original state. In other words, given infinite time, your cup of cold coffee should someday reheat itself. Both objections cut to the heart of Boltzmann's idea. If the microscopic laws are time-symmetric, how can macroscopic irreversibility emerge at all? Boltzmann's answer was subtle but profound. The arrow of time doesn't come from the laws, it comes from initial conditions. If the universe began in a state of extremely low entropy, then the overwhelming majority of microscopic motions would inevitably lead toward higher entropy. The direction of time, then, is not dictated by physics, but by the unlikeliness of where it all started. It's as if we find ourselves standing on a mountain peak of improbability, looking down into a vast valley of possible states. Gravity doesn't need to push the rock downhill. The shape of the landscape ensures that's the way it will roll. Boltzmann's logic was impeccable, but unsettling. It implied that everything, the cooling of stars, the fading of memory, the flow of history, might be a consequence of an initial cosmic coincidence. And if that's true, it opens a door to a deeply strange possibility. Suppose the universe isn't a single story with a beginning and an end, but an eternal sea of chaos, an infinite expanse of particles exploring every possible configuration. In such a sea, rare pockets of order, low entropy fluctuations, would occasionally form simply by chance. One of those fluctuations might resemble a universe like ours. That's the idea behind the Boltzmann universe, or more famously, the Boltzmann brain paradox. If the cosmos is infinite and eternal, and every configuration happens eventually, then the most probable way to get a self-aware observer isn't to form an entire orderly universe. That's far too improbable. The most probable way is for a single brain, complete with false memories and perceptions, to momentarily assemble itself from chaos. A conscious mind, floating in disorder, hallucinating a universe that never existed. It sounds absurd, and it is. But statistically, it's hard to rule out if the universe really explores all possible states forever. This thought experiment disturbed physicists and philosophers alike. It challenges not only cosmology, but the very concept of knowledge. If the laws of probability make Boltzmann brains more likely than entire histories like ours, then how can we trust that we're not one of them? Brief sparks of order, dreaming of laws and stars. Of course, Boltzmann himself never intended such interpretations. He was a physicist, not a mystic. Yet his equations led inevitably to these philosophical abysses. They force us to confront a question both absurd and strangely profound. Are we just low entropy fluctuations having thoughts about order? It's the kind of question that only physics can make sound like poetry. Still, before wandering too far into speculation, it's worth grounding ourselves in what Boltzmann truly accomplished. His statistical approach gave the second law of thermodynamics a backbone, a reason. It explained why entropy increases not as fate, but as mathematics. At its core, his work told us this: the microscopic world doesn't decide which way time flows. It merely explores possibilities. The apparent arrow emerges because, out of all possible configurations, those with higher entropy dominate. That's why we experience time moving forward, not because nature prefers it, but because we happen to live in a universe that started improbably ordered and is still unraveling. It's like opening a deck of cards that was once perfectly stacked, ace to king, suit by suit, and beginning to shuffle. With each shuffle, order dissolves into randomness. You could, in principle, shuffle your way back to order, but the odds are so impossibly small that it might as well never happen. Boltzmann saw the universe that way, an unimaginably large deck, shuffling itself since the beginning of time. Each moment we experience is just one configuration among uncountable others. His contemporaries struggled with this way of thinking. In the 19th century, physics had been a world of certainties, deterministic, clockwork, exact. Boltzmann replaced that certainty with probability, with the idea that even the laws of nature might only describe what is likely to happen, not what must. Today, that idea feels natural. It's the foundation of quantum mechanics, statistical mechanics, and even information theory. But in Boltzmann's time, it was revolutionary. It was as if he'd discovered that the universe had dice, and they never stop rolling. There's something both humbling and liberating in that view. We too are products of statistical chance, islands of temporary order in a sea of randomness. Our memories, our civilizations, even the structure of galaxies are fleeting arrangements, unlikely but not impossible. Entropy doesn't erase meaning, it gives it context. The fragility of order is what makes it precious. Boltzmann once said, "The struggle for life is not a struggle for raw materials, those are everywhere, nor for energy, which exists in abundance, but a struggle for entropy, for the right to structure energy into improbable forms." He might have been talking about biology, but it applies to everything, even thought. Every idea, every spark of awareness is a small reversal of equilibrium, a defiance of stillness that leaves the universe slightly more disordered than before. So when you think about entropy, Don't imagine a march toward ruin. Think of it as the breathing of the cosmos, a constant balancing act between the improbable and the inevitable. Boltzmann's equations gave time its meaning, but they also gave existence its poetry. They remind us that order is temporary, but never wasted. It's the brief shimmer of possibility against the endless backdrop of chance. And somewhere, in that dance between chaos and structure, between microstates and macrostates, between certainty and probability, we find ourselves fleeting arrangements of matter, trying to understand why everything changes, yet something endures. Perhaps that's the most beautiful paradox of all. For most people, entropy sounds like a physicist's obsession, a word whispered over diagrams of gases and pistons. But the truth is far more profound. Entropy isn't confined to steam engines or laboratories. It governs everything that changes, everything that grows, everything that thinks. It is the quiet accountant of existence, tracking every transfer of energy, every act of transformation, from the melting of glaciers to the firing of neurons. And if you look closely enough, you find its signature in the structure of life itself. The living world seems, at first glance, to defy entropy. Life builds order, cells organize themselves, DNA replicates, ecosystems bloom from chaos into harmony. It's easy to think that life is somehow against the second law, that it's the universe's rebellion against decay. But that's not quite true. Life doesn't fight entropy. It uses it. In the 19th century, as scientists were grappling with thermodynamics, this paradox puzzled even the sharpest minds. How could something so complex, so improbably structured, emerge in a world supposedly sliding toward disorder? The answer lies in how entropy really works. The second law doesn't say that order cannot exist. It says that total entropy in a closed system must increase. Life, however, is not a closed system. It is open, constantly exchanging energy with its surroundings. A living cell, for instance, maintains its internal order by taking in low entropy energy, sunlight, food, chemical gradients, and releasing high entropy waste, mostly as heat. From the perspective of the universe as a whole, entropy still rises, but locally, within that brief flicker of a living organism, order blossoms. It's like a candle flame, bright, structured and temporary, feeding on a source of energy and leaving behind exhaust and heat. Life is the same, a flicker in thermodynamic balance, beautiful precisely because it cannot last. In the early 20th century, chemists began to see this more clearly. Biological processes, from metabolism to photosynthesis, are all little engines, converting one form of energy into another. When your body digests food, it's not just extracting nutrients, it's turning chemical energy into organized motion, a cascade of molecular transactions that power your heartbeat, your breath, your thoughts. Yet, with every heartbeat, a little more entropy is produced. Every act of living, every blink, every neuron firing, adds a tiny whisper of disorder to the universe. It's almost poetic. We exist by accelerating the universe's slow drift toward equilibrium. The physicist Erwin Schrödinger, better known for his quantum cat, explored this paradox in his 1944 book, What is Life? He proposed that living things feed on what he called negative entropy. By consuming organized energy, like sunlight or food, they sustain their internal order. In his words, the organism feeds upon negative entropy. We call it energy, but at its core, it's information, a difference, a gradient, a potential that hasn't yet been spent. That idea would turn out to be more than poetic language. It hinted at one of the most surprising discoveries in modern physics, the deep connection between entropy and information. The first glimmer of this connection came from a thought experiment, one that, at first, seemed to threaten the entire foundation of thermodynamics. In 1867, The great Scottish physicist James Clerk Maxwell, the man who unified electricity, magnetism, and light, imagined a tiny creature, later called Maxwell's demon. The demon sits in a box divided by a wall with a small trapdoor in the middle. On one side is warm gas, on the other, cold gas. The demon's job is simple. It observes individual gas molecules and, whenever a fast, hot one approaches from the cold side, it opens the door to let it through, and does the opposite for slow, cool molecules. After some time, the demon would have sorted the molecules so that one side becomes hotter and the other colder, seemingly creating a temperature difference without expending any work. In other words, the demon would have violated the second law of thermodynamics, a perpetual motion machine powered only by cleverness. It was a brilliant provocation, a tiny creature that could, in principle, reverse entropy with nothing but observation. For decades, no one could quite explain what was wrong with the idea. The demon became a favorite puzzle of physicists, a mischievous challenge lurking in the equations. Then, almost a century later, the answer emerged from an entirely new field: the science of information. In the mid-20th century, American engineer Claude Shannon revolutionized communication with his 1948 paper, A Mathematical Theory of Communication. Shannon introduced a new way to measure uncertainty, the amount of information in a message, and called it, coincidentally, entropy. He had rediscovered Boltzmann's mathematics in an entirely different domain. Where Boltzmann's entropy measured the number of microscopic arrangements of atoms, Shannon's measured the number of possible messages in a signal. Both were measures of uncertainty, of how many configurations were possible. That connection between physical and informational entropy was more than analogy. It hinted that information itself is physical. And in 1961, physicist Rolf Landauer made that idea explicit. Landauer proposed a principle that now bears his name. Erasing information has a thermodynamic cost. Whenever a computer deletes a bit, resetting it from 1 or 0 to a blank state, it must dissipate a tiny amount of energy as heat. It doesn't matter what kind of computer it is, mechanical, electronic, quantum, or hypothetical. The act of forgetting always raises entropy. In other words, information is not free. Every memory stored, every computation performed, every decision made, all have an energy price. Even the universe's own bookkeeping cannot be done without paying the tax of heat. This insight retroactively saves the second law from Maxwell's demon. Yes, the demon can observe and sort molecules, but to do so, it must store information, remembering which molecule is fast or slow. Eventually, it has to erase those memories to keep working. And when it does, it releases heat, restoring the entropy it seemingly removed. No law was broken. The universe keeps perfect accounts. It's astonishing how this simple principle extends beyond machines and molecules, right into the realm of mind. Consider your own brain. Every thought you form, every memory you store, is a physical event. Neurons fire, ions flow, molecules shift. To remember something is to alter the configuration of matter, and to erase something is to increase entropy somewhere in your neural web. The physicist John Wheeler once put it beautifully: it from bit. He meant that everything physical, every it, ultimately arises from information, from bits. The universe, in that view, is not just a machine made of particles, but a computation made of relationships and distinctions. When you think, you are processing entropy. When you forget, you are releasing it. When you live, you are converting low entropy energy into the improbable structure of awareness, and in doing so, you warm the cosmos by an infinitesimal degree. It's an almost sacred symmetry. Life, intelligence, even consciousness are forms of organized complexity that feed on gradients. on differences between what is known and what is unknown, what is ordered and what is chaotic, and entropy is the measure of that difference dissolving. The deeper you go, the more you see entropy as the language of existence. In chemistry, it explains why reactions happen, why salt dissolves in water, why ice melts, why iron rusts. Each process increases the number of accessible microstates, expanding the system's entropy. In biology, it explains why evolution favors efficiency, not because nature seeks perfection, but because survival depends on managing energy flows and entropy production. The fittest organisms are those that best channel the thermodynamic river. Even our technologies, from microchips to massive data centers, are just elaborate ways of shuffling entropy around, concentrating order in one place while dumping heat into another. Every glowing screen is a small sun of waste energy, each computation a flicker of cosmic disorder. In this way, entropy ties together the mechanical, the biological, and the digital, three faces of the same story. It's tempting to see all this as bleak, as if the universe were a great machine grinding toward exhaustion. But perhaps it's the opposite. Entropy is not destruction, it's transformation. It's the condition that allows change, evolution, creativity. Without entropy, there would be no gradients, no flow, no drive for anything to happen. The universe would be static, cold, silent, and dead. Entropy gives life its fleeting beauty precisely because it guarantees that nothing lasts forever. Even memory, that most human of abilities, is born of impermanence. You remember something because it was once different. You think because the world is not yet in equilibrium. Entropy is the quiet backdrop that makes experience possible. Every moment, you are surrounded by it. In the warmth of your breath, the light from your screen, the tiny electrical storms inside your mind. Each is a trade, a balancing act, a movement from improbability to probability. And though the universe may seem vast and indifferent, there's something deeply intimate about this law, because every act of understanding, every spark of awareness, every fleeting realization that passes through your thoughts, all of it leaves the cosmos just a little more disordered than before. And yet, in that process, meaning emerges. Entropy governs everything, from the fires in stars to the flicker of human thought. It's the hidden rhythm beneath chemistry, biology, computation, and consciousness. It does not fight us, and we do not fight it. We dance with it, briefly, beautifully, in the thin space between order and decay. And somewhere in that dance, between memory and forgetting, between creation and dissolution, the universe contemplates itself, for a moment, before drifting once again into the quiet sea of probability. Entropy began, as far as we can tell, with a bang, not a chaotic one, as the phrase Big Bang suggests, but an extraordinarily smooth one. That paradox sits at the center of modern cosmology. The birth of the universe was both the greatest explosion imaginable and, somehow, the most uniform moment in history. If entropy measures disorder, the spreading and mixing of energy, then the early universe should have been a high-entropy mess. Yet it wasn't. The first few seconds after the Big Bang were astonishingly ordered. Matter and energy were distributed with incredible evenness, the cosmic equivalent of a freshly ironed sheet. Tiny fluctuations, 1 part in 100,000, rippled through the early plasma, but on the whole, it was smooth, hot, and simple. And that simplicity is the mystery. If the second law says entropy always increases, why did everything start so low? The answer is both subtle and profound, and it begins with a shift in how we think about what order means when gravity is involved. In the days before cosmology became a precise science, physicists thought of entropy mostly in terms of mixing and spreading, gases expanding, heat diffusing, molecules randomizing. But gravity changes the rules. In ordinary systems, uniformity means high entropy. A cup of coffee evenly mixed with milk is more disordered than one with distinct layers. But in a universe dominated by gravity, it's the opposite. A perfectly smooth distribution of matter actually represents low entropy, because gravity loves to clump. A gas cloud in space, for instance, can collapse under its own gravity to form a star. When it does, gravitational potential energy is converted into heat and radiation. The star shines, and the total entropy increases. The clumping produces structure, but that structure is accompanied by more overall disorder. It's counterintuitive. In the cosmic context, order looks like chaos, and chaos looks like order. Smoothness is rare and fragile. Lumpiness is inevitable. This inversion explains why the early universe's uniformity was so extraordinary. It was a low entropy starting point, a cosmic deck stacked improbably in perfect arrangement. From that improbable order, gravity began its slow and inevitable work of creating structure: stars, galaxies, planets, and eventually, us. Every galaxy in the night sky is a monument to increasing entropy. Each formed as matter fell together, heating up, radiating energy, and raising the total disorder of the cosmos. It's easy to forget that the heavens, those serene, glittering lights, are, thermodynamically speaking, the byproducts of collapse and waste. Every star is a furnace converting nuclear fuel into heat, light, and entropy, pouring it into the cold darkness of space. And yet, that same waste drives everything we know. The sunlight warming your face, the photons that power photosynthesis, the chemical energy that fuels life, all of it is entropy in motion, cascading down the great thermodynamic slope from hot to cold. The Earth is not isolated, it is a conduit. It receives low entropy energy from the sun, concentrated, organized light, and emits higher entropy infrared radiation back into space. The difference fuels winds, oceans, ecosystems, and civilizations. Every gust of wind, every leaf unfurling in spring, every act of thought depends on that steady imbalance, the slow leak of order into the void. On the largest scales, the same story continues. The universe itself is an engine. As it expands, space stretches, stars burn, galaxies collide, and entropy grows. But cosmic entropy isn't just about heat, it's about information. The expansion of space increases the number of possible configurations for matter and energy. As galaxies drift apart, each region becomes more isolated, its contents less able to interact or exchange information. The universe, in effect, becomes more forgetful with time. We can already see this happening. Distant galaxies are receding so fast that their light will eventually slip beyond the horizon of visibility, redshifted until it fades into darkness. The night sky, once ablaze with billions of stars, will someday grow empty. As the universe ages, stars will exhaust their fuel and die. The bright era of starlight will give way to what cosmologists poetically call the degenerate era, a time dominated by remnants, white dwarfs, neutron stars, black holes. These corpses of matter will continue radiating faintly for unimaginable spans of time, slowly cooling toward the background temperature of space. Entropy, ever the patient accountant, will continue its tally. Eventually, even black holes, the ultimate sinks of entropy, will fade. In 1974, Stephen Hawking made a remarkable discovery. Black holes aren't completely black. They emit a faint radiation due to quantum effects near their event horizons. Over vast timescales, 167 years for a typical stellar black hole, they evaporate away, releasing their stored entropy back into the cosmos. Hawking also showed that a black hole's entropy is proportional to the area of its event horizon, not its volume, a discovery that connected gravity, quantum mechanics, and thermodynamics in a single equation. In simple language, he revealed that the universe keeps its most detailed records on surfaces, not in volumes. It's as though every boundary in space, every horizon, stores the information of everything that falls within it. The deeper implication, hinted at by later theories like the holographic principle, is that perhaps the entire universe is, in some profound sense, a vast projection, a cosmic hologram, its information encoded on a boundary we cannot yet fully perceive. Whether that's true or not, Hawking's insight cemented one idea: entropy is not a side effect of the cosmos. It's one of its fundamental dimensions, and so the story of the universe is the story of entropy's slow ascent. From the uniform glow of the Big Bang to the tangled web of galaxies today, entropy has been the hidden sculptor, carving structure out of imbalance, driving evolution and decay alike. But where does it all lead? If the second law holds, then the universe's fate seems grimly certain. As expansion continues and energy sources dwindle, the cosmos will approach thermal equilibrium, the ultimate flattening of all gradients. No hot, no cold, no light, no dark, no structure, no change. This is the so-called heat death, not an explosion, but a fading, a cosmic sigh into uniformity. It's a strange kind of ending because it's not destruction, it's completion. The universe won't collapse or explode. It will simply stop doing anything interesting. Every atom will have lost its story. Every star, every black hole, every spark of thought will have dissolved into a smooth bath of photons at nearly absolute zero. Time, as we understand it, may lose its meaning, because time's arrow is tied to entropy. Once everything has reached maximum entropy, when no further change can occur, time itself becomes directionless. The river still exists, but it no longer flows. It's almost unbearable to imagine. A universe so vast and ancient that even decay has ended. And yet, there is a strange beauty in it too. For billions of years, energy has rushed downhill, from hot to cold, from concentrated to diffuse, from potential to memory. And in that rush, everything we know has happened. Stars, planets, life, thought, art, all are side effects of the universe relaxing. Entropy doesn't just end things, it makes them possible. If the universe began already at equilibrium, nothing could have ever happened. The dance of order and disorder, of formation and dissolution, is the very essence of existence. The philosopher Arthur Eddington once remarked that the second law of thermodynamics holds the supreme position among the laws of nature. If your theory is found to be against the second law, there is nothing for it but to collapse in deepest humiliation. But beyond the humor of that warning lies something profound. The second law is not just a rule about heat, it's a reflection of the deep asymmetry that allows reality to unfold. Entropy is not chaos. It's the memory of transformation. It is the record of every star that ever burned, every atom that ever cooled, every moment that ever passed. So when cosmologists speak of the universe ending in heat death, it's not really a death in the ordinary sense. It's the culmination of a long story, the stillness after the final note of a symphony. The universe won't end in fire or in ice, as the poets imagined, but in quiet balance. The embers of creation will cool into harmony, not ruin. And perhaps, if there is something beyond physics, if consciousness or meaning has a place beyond entropy, that final stillness won't be emptiness, but completion. A moment when the universe, having burned through all its improbable miracles, finally rests, not defeated, but fulfilled. If you were to stand at that distant horizon of time, unimaginably far beyond the lifespan of stars, beyond memory, beyond motion, you wouldn't see chaos. You'd see silence, a cosmos at peace with itself, every gradient gone, every imbalance resolved. It wouldn't be the end of something beautiful. It would be the quiet echo of everything that ever was. If you were to watch a movie of a ball rolling across a table, you'd know instantly which direction time was flowing. The ball slows down, friction drains its energy, and it comes to rest. Reverse the footage, and it looks absurd. The ball leaps into motion, gaining speed without cause. Your intuition says that's not how the world works, and yet, according to the fundamental laws of physics, it is how the world works. At least, it could be. The strange truth is that almost every equation that governs the universe works perfectly well if you reverse time. If you swapped forward for backward, the laws wouldn't protest. In the 17th century, Isaac Newton's laws of motion changed the world. His equations told us how objects move and accelerate, how planets orbit, and how forces interact. But these equations don't contain any preferred direction of time. If you were to run the cosmic film backward, planets would still trace perfect ellipses, apples would rise to their branches in mathematically consistent ways, and the equations would remain entirely valid. This property, called time symmetry, means that, in Newton's universe, the arrow of time doesn't come from the laws themselves. It comes from something else, something hidden in the background conditions. A century and a half later, James Clerk Maxwell wrote down his equations for electricity and magnetism, another towering achievement. Maxwell's equations unified light, magnetism, and electricity into one elegant framework, showing that light itself is an electromagnetic wave. They, too, are perfectly reversible. Play them backward, and you'd see electromagnetic waves converging into the filament of a light bulb, feeding energy into it instead of radiating out. Mathematically, nothing forbids it. And even in the 20th century, when Erwin Schrödinger introduced his equation to describe the evolution of quantum systems, the same symmetry held. The wave function, the mathematical ghost that encodes all possible states of a particle, evolves deterministically forward and backward. If you flipped time in Schrödinger's equation, it would still make sense. So at every scale, classical, electromagnetic, quantum, the fundamental dynamics of nature appear time-symmetric. Nothing in those equations requires time to flow one way rather than the other. This presents a profound contradiction between mathematics and experience. In equations, an egg can unbreak. In life, it cannot. So where does the asymmetry come from? Physicists have spent more than a century chasing that question, and their answers lead into some of the strangest corners of science, places where symmetry, probability, and existence itself begin to blur. One of the deepest symmetries known to physics is called CPT symmetry, short for charge, parity, and time. It's a mouthful, but the idea is surprisingly elegant. CPT symmetry says that if you flip the universe in three specific ways, reverse all charges, positive to negative and vice versa, mirror all spatial coordinates as though reflected in a cosmic mirror, and reverse the flow of time, then the underlying physics remains exactly the same. In other words, a CPT-reversed universe would be physically indistinguishable from ours. A mirror-image cosmos, running backward in time with inverted charges, would obey identical laws. This is one of the bedrock principles of quantum field theory, tested, confirmed, and respected like a sacred rule of the cosmos. Yet within that symmetry lies a subtle asymmetry. If you apply only one of those flips, say just reversing time without flipping charges or mirror directions, certain phenomena break the pattern. For example, in the 1960s, physicists studying the decay of particles called kaons discovered that their behavior slightly violated a related symmetry known as CP symmetry, the combination of charge and mirror reflection. The violation was tiny but real, and if CP symmetry is broken, then by CPT's grand rule, time reversal symmetry must also be broken. That discovery shocked the scientific world. It meant that, at the level of subatomic particles, time is not perfectly symmetric after all. But before we rush to imagine eggs reassembling or teacups unshattering, it's important to note that this asymmetry is subtle, almost vanishingly small. The CP violation in kaons affects only specific types of particle interactions, and only under extreme conditions. It doesn't influence the everyday physics of tables, stars, or human lives. In our world, where trillions upon trillions of particles interact chaotically every second, the second law of thermodynamics still rules absolutely. The tiny cracks in time symmetry that we see in particle physics are more like fingerprints, delicate traces hinting that the universe itself might carry a slight preference for one direction. Still, scientists have tried to push this question further. Could we ever see time run backward, even in miniature? The first step toward that question came not from cosmology, but from chemistry and molecular physics. At small scales, where fluctuations matter, the second law isn't as rigid as it seems. In the 1990s and early 2000s, experiments using tiny systems, like colloidal particles trapped in laser beams, revealed something fascinating. If you isolate a microscopic object and watch it for long enough, you occasionally see it perform small violations of the second law. A particle, buffeted by random thermal motion, might spontaneously move against the usual gradient of entropy, getting hotter instead of cooler, or moving uphill instead of down. For a brief moment, it's as if time hiccups. But these events are fleeting, and the larger the system, the rarer they become. In macroscopic terms, for objects made of billions of particles, such reversals are astronomically improbable. This discovery gave rise to a principle called the fluctuation theorem, which quantifies the probability of these temporary reversals. It shows that the second law is not absolute in small systems, it's statistical. Given enough time, the unlikely can happen. In other words, the arrow of time is not written in stone, it's written in statistics. The direction we experience is the overwhelmingly probable one. In a sense, the entire universe is a colossal experiment in probability. Every moment of forward time is just the most likely way events can unfold, given the staggering number of particles involved. Reverse the film at the atomic level, and nothing truly breaks. Reverse it at the human scale, and everything does. That difference between what's possible and what's probable is what makes our experience of time so distinct. When you drop an egg, trillions of molecules spread out in countless ways. The number of microstates available to the shattered egg is unimaginably greater than those available to the intact one. So while it's theoretically possible for those molecules to come back together, the odds are so unfathomably small that they may as well be zero. To witness time running backward, we'd have to wait longer than the universe has existed, and even then we'd need infinite patience. Still, physics has a strange sense of humor. While we can't reverse time in the macroscopic world, some quantum experiments come remarkably close. In 2019, a team of scientists working with IBM's quantum computer simulated a process akin to time reversal. They programmed a few qubits, quantum bits, to evolve forward under specific conditions, then mathematically applied an operation that reversed their evolution. For a fleeting instant, the qubits seemed to rewind, returning to an earlier state. It wasn't actual time travel, of course, just a controlled reversal of a quantum system's dynamics, but it showed, once again, how reversible the fundamental laws really are. At the deepest level, time's direction isn't a rule, it's an illusion born from complexity. When we ask whether time could run backward, we're really asking something about ourselves. Would backward time feel any different if the underlying laws didn't care? Imagine a world of just two particles. They move, collide, exchange energy. If you reversed the direction of time, the scene would look identical. There's no sense of before or after. Now imagine a world of 10 particles, or 1,000, or 1 billion. Patterns emerge. gradients, flows, causes, effects. Suddenly, there's history. The collective behavior creates asymmetry, even if each individual interaction remains reversible. Time's arrow, then, might not be fundamental at all. It may be an emergent property, something that arises only when vast numbers of particles interact, when memory and causality begin to mean something. We perceive time as moving forward because our brains, our lives, our entire existence are built from systems that grow more entropic. Our memories are laid down in one direction. Our biology only runs one way. Entropy, in that sense, doesn't just describe the arrow of time, it creates it. Could we ever truly reverse it? Probably not. Not because the laws forbid it, but because the universe is too vast, too tangled in its own improbability. The film of existence can, in principle, be played backward, but we are bound within the frame. Our bodies, our memories, our thermodynamic engines all run on gradients that flow one way. We are, in every sense, creatures of entropy. And maybe that's what gives meaning to the direction of time, that we are built from irreversible processes, yet capable of understanding the symmetry beneath them. We are entropy made self-aware. When you think about it that way, the arrow of time isn't something to fight against or fantasize about reversing. It's the current that carries us, the statistical whisper of the universe saying, this way is more likely. And we, floating on that current, mistake it for destiny, when it's really just probability wearing the mask of fate. Time, as physics describes it, is impartial. It has no preferred direction, no empathy for beginnings or ends. But to human beings, time is anything but neutral. We live inside its flow, and it defines us. We remember the past, but not the future. We recall yesterday's breakfast, but not tomorrow's dinner. We can trace our childhood in vivid snapshots, but the years ahead are blank pages, written only when we arrive. That asymmetry, the way memory works in one direction, is one of the most intimate consequences of entropy. It is the psychological arrow of time, the way the universe's thermodynamic current flows through consciousness itself. The human mind is a machine built from entropy. Every thought, every memory, every neuron that fires does so by consuming energy and creating heat, by increasing the universe's disorder, however slightly. When your brain recalls an event, it doesn't simply retrieve a file, it reconstructs a pattern. Neurons reshape their connections, biochemical signals cascade, electrical charges pulse through microscopic networks. That act of remembering requires work, and work produces entropy. In a sense, memory is irreversible. Once a network of neurons has changed, it cannot go back to what it was. The old configuration is gone, replaced by a new one that carries the trace of the past. That's why we remember the past and not the future. Memory itself is a thermodynamic process that leaves a trail in one direction. To remember the future, we'd have to form traces of events that haven't yet happened, and that would mean our brains already contained information about states that don't yet exist. The universe, as far as we know, doesn't allow that. Our perception of time's flow is built on these microscopic irreversibilities. Every action that consumes energy, every synaptic event, reinforces the arrow of time. But memory isn't just a neurological mechanism, it's also the root of identity. Who we are depends entirely on what we remember. Without the past, we'd have no sense of continuity, no thread connecting the person we were with the person we are now. And memory's one-way nature gives our lives their direction. It allows cause and effect to make sense. We remember causes, not consequences. We anticipate outcomes, not origins. If time flowed the other way, if entropy decreased, our experience of life would unravel. We'd watch shattered glasses leap together, smoke flow into candles, and people grow younger. But more strangely, our memories would reverse too. We'd remember events that hadn't yet occurred, while forgetting those that already had. In that inverted world, nothing would feel strange, because our consciousness would flow in sync with the reversed entropy. We'd still think we were moving forward. It's unsettling to realize that our sense of forward isn't a universal truth. It's just alignment with the dominant direction of entropy. The link between memory and causality runs deep. In a universe governed by reversible laws, the only thing that defines cause and effect is the asymmetry of entropy. Causes are events that lower entropy locally. They create order. Effects are the consequences that increase it again. You strike a match. Energy concentrates in the tip. Order briefly rises, and then the flame spreads, releasing heat and smoke. The match caused the fire, not because physics demanded that direction, but because entropy made it more likely. So even the structure of reason, the way we understand stories and sequences, may be an echo of thermodynamics. Our language, our logic, our concept of before and after, all of it may rest on the same asymmetry that governs heat and energy. When we say the chicken came before the egg, we're really saying entropy flowed this way. Human emotion, too, is built on irreversibility. Regret, nostalgia, loss, they all depend on the one-way flow of experience. You cannot unsay a word, unage a child, or unlive a moment. That finality, painful as it is, gives our emotions their weight. A world without entropy would be a world without meaning, because meaning arises from change, from the passage of time and the impossibility of reversal. Love, for instance, draws its beauty from fragility. We love because we know we will lose. Every shared moment carries the quiet awareness that it will never repeat exactly the same way. Entropy guarantees that every kiss, every sunset, every heartbeat is unique, a configuration of atoms that will never come again. There's something profoundly human about that. We find value in the ephemeral precisely because it fades. If time were a loop, endlessly repeating without loss, our emotions would flatten. Passion would be irrelevant, regret impossible, hope meaningless. Entropy gives us tragedy, but also tenderness. It makes us care. Nowhere is the connection between entropy and human life more visible than in aging. From the moment we're born, our bodies begin to accumulate microscopic irreversibilities. Cells divide, DNA replicates imperfectly, proteins misfold, oxidative stress damages molecules. Each process is governed by the same thermodynamic law. Order requires work, and work produces entropy. Life maintains itself by exporting disorder, by burning energy to keep internal systems organized. But over time, inefficiencies accumulate, waste builds, repair mechanisms fail. The balance tips. Aging, in thermodynamic terms, is the gradual loss of a system's ability to keep local entropy low. It's not a failure of design, it's the inevitable outcome of the second law. Even when we eat, breathe, and rest, we're engaged in a constant negotiation with entropy, temporarily keeping it at bay inside our bodies by producing more of it outside. But eventually, the cost becomes too high. When biological systems can no longer offset their own disorder with external exchanges, life slips quietly toward equilibrium, the same stillness that waits at the end of the universe. It's a humbling symmetry. The same law that governs the cooling of stars governs the cooling of bodies, yet there's a quiet beauty in that too. Our mortality is not a cosmic accident. It's the natural expression of the same principle that makes stars shine, rivers flow, and galaxies spin. Entropy isn't the enemy of life, it's the condition for it. Without entropy, there would be no metabolism, no evolution, no thought. To live is to burn gradients, to turn difference into motion, order into awareness. And while our bodies age, our consciousness transforms that inevitability into meaning. We tell stories about time precisely because we cannot escape it. The physicist Carlo Rovelli once wrote, "The world is not a collection of things, it is a collection of events." We are among those events, transient, self-aware patterns in a sea of transformations. Entropy ensures that we will end, but it also ensures that we happened. We are improbable. Think of a single moment, something utterly ordinary. A morning cup of coffee, steam rising against the light. That scene, simple as it is a masterpiece of entropy at work. The heat from the cup flows into the air. Molecules scatter, carrying away energy. The aroma disperses through the room. The steam, shaped by turbulence, curls and fades. In seconds, that particular arrangement of atoms, that exact pattern of warmth, scent, and light, will be gone forever. And yet, because of that loss, you perceive the moment as fleeting, precious, alive. Entropy doesn't just make moments perish, it makes them matter. It transforms the infinite possibility of the universe into a single, unrepeatable now. In this way, physics touches something emotional, even spiritual. The same equations that describe heat flow and particle motion also describe our awareness of passing time, our nostalgia for what's gone, our longing for what can't return. We are thermodynamic beings, aware of our own irreversibility. We carry the arrow of time not just in our memories, but in our cells, our breath, our stories. Perhaps that's why we invent rituals, photographs, art, desperate little machines to freeze the irreversible, to cheat entropy for a heartbeat longer. But even those efforts produce entropy too. More ink, more sound, more photons scattered into space. In the end, we can't stop time. We can only learn to see beauty in its direction, because every loss is proof that we existed long enough to love. Every wrinkle is evidence of motion, every memory the residue of a moment that mattered. Entropy gives us the arrow of time, and with it, the capacity for meaning. The human experience is, at its core, a thermodynamic journey. We rise from order, burn brightly through imbalance, and return to equilibrium. But along the way, we do something remarkable. We feel. We turn the impersonal drift of entropy into art, into memory, into compassion. If the universe could feel, perhaps this is exactly what it would feel like. To know it is changing, to understand that everything beautiful is temporary, and to love it all the more for that. And maybe, in that sense, we are the universe remembering itself, briefly, warmly, before the light fades back into stillness. If the arrow of time feels solid in our daily lives, quantum mechanics quickly dissolves it into mist. At the scale of atoms, molecules, and subatomic particles, time seems to behave with eerie indifference, flowing forward or backward without preference, like a film that makes sense in either direction. And yet, somewhere between the quantum world and our human one, direction reappears. The smoke leaves the candle, not the other way around. We age, we remember. Events unfold one way only. So where, in all that strangeness, does the arrow of time actually emerge? In 1926, Erwin Schrödinger wrote an equation that would become one of the most famous in all of science, the Schrödinger equation. It describes how the wave function of a system evolves through time. The wave function is the mathematical heartbeat of quantum mechanics, a shimmering map of probabilities rather than certainties. It tells us where a particle might be, what energy it might have, what spin or momentum it might show when measured. The equation is beautifully reversible. If you take a wave function at one moment and evolve it forward, you get a new state. Evolve it backward, and you return to the old one. Nothing in the equation itself singles out a direction for time. But then we observe something, and everything changes. When a measurement is made, the wave function appears to collapse. Out of a haze of possibilities, one outcome becomes real. The particle is here, not there. The cat is alive, not both alive and dead. And that collapse, that sudden, irreversible reduction of probability to actuality, seems to defy the symmetry of the Schrödinger equation. It's the quantum equivalent of entropy, a process that cannot be undone. Once a measurement has been made, the information about the superposition is gone. So, at least on the surface, quantum mechanics contains two kinds of time: the smooth, reversible evolution described by the Schrödinger equation, and the abrupt, irreversible collapse that occurs when observation happens. Reconciling those two descriptions has haunted physicists for a century. In 1927, Niels Bohr and Werner Heisenberg proposed what became known as the Copenhagen interpretation, still the most widely taught, if not universally loved, version of quantum mechanics. According to Bohr, the wave function doesn't represent physical reality itself, but our knowledge of it. Before measurement, there is no definite outcome, only potential outcomes. Reality, in this view, doesn't crystallize until interaction occurs. That interaction, between system and observer, is what introduces irreversibility. Before observation, the universe hums along symmetrically. After it, the symmetry breaks. But who or what counts as an observer? Is consciousness required? Does a photon bouncing off an atom count as a measurement? Bohr would have shrugged and said, "Don't ask." Quantum theory, he argued, tells us what we can say about nature, not what nature is. Not everyone was satisfied with that. Albert Einstein famously protested, "God does not play dice." He believed the randomness of quantum mechanics masked some deeper, hidden order, variables not yet discovered that could restore determinism. Erwin Schrödinger himself wasn't fond of Bohr's interpretation either, which is why he created his famous thought experiment of the cat in the box, both alive and dead, until observed. He intended it as a parody, not a mystery. But the paradox stuck, and generations of students have since been haunted by that poor imaginary feline. As experimental precision improved, new ways to think about time in quantum mechanics began to emerge. One of the most important ideas is decoherence, a process that explains why we don't see superpositions in the macroscopic world. When a quantum system interacts with its environment, say, an atom colliding with a stray photon or air molecule, the delicate correlations that define its superposition become scrambled. The system's quantum coherence leaks into the environment, dispersing its information into countless degrees of freedom. To us, it looks as if the wave function has collapsed, but in truth, the information has simply become inaccessible. Like a drop of ink diffusing into water, it's still there in principle, but no longer recoverable. That loss of coherence, that spreading of quantum information, is a kind of entropic process. Each interaction increases the entropy of the combined system. In this view, the arrow of time in quantum mechanics arises not from measurement per se, but from the same principle that governs steam engines and dying stars, the irreversible growth of entropy. When a particle becomes entangled with its surroundings, its pure low-entropy state transforms into a messy, high-entropy mixture. And because there are so many possible configurations of the environment, reversing the process becomes effectively impossible. The laws remain symmetric, the outcomes do not. This connection between entropy and quantum measurement has led some physicists to wonder whether time itself might be an emergent phenomenon, not a fundamental feature of the universe, but a statistical one. In a timeless quantum world, what we call time's flow could simply be the accumulation of entanglement, the progressive loss of information from system to environment. Each moment is defined by what has decohered and what has not. As physicist Carlo Rovelli suggests, the flow of time might not be something that exists independently, but a relational property, something that appears only when systems interact. In that sense, the arrow might be born in the act of observation, in the exchange of information that entangles the observer and the observed. Of course, the Copenhagen interpretation isn't the only game in town. Quantum theory, like philosophy, is rich in competing worldviews, each one an attempt to restore coherence to a theory that seems to deny it. The many worlds interpretation, proposed by Hugh Everett in 1957, eliminates wave function collapse entirely. According to Everett, every quantum possibility actually happens, just not in the same universe. When you measure a particle, the universe splits. One branch where the particle is here, another where it's there. You experience only one branch, but all are equally real. In that framework, the Schrödinger equation reigns supreme, perfectly reversible and timeless. So where does entropy fit into that picture? Interestingly, even in many worlds, each branch experiences its own arrow of time, because decoherence still occurs within each universe. The branches themselves separate irreversibly, and the information connecting them becomes hopelessly scrambled. In other words, entropy doesn't vanish, it multiplies. Then there are retrocausal models, which flirt with the unthinkable, that effects might influence causes. These theories suggest that the future could, in subtle ways, shape the present. The equations of quantum mechanics, after all, don't forbid it. In the transactional interpretation, for example, waves travel both forward and backward in time, forming handshakes between emitter and absorber. What we perceive as a one-way transaction might actually be a negotiation between past and future. If true, and it's a very big if, then our sense of cause and effect might be only half the story. The arrow of time could be a matter of perspective, like seeing just one side of a coin. But before diving too deep into paradox, it's worth remembering that every interpretation must still obey the same thermodynamic reality. No matter how quantum the world gets, entropy remains undefeated, even if time can, in principle, run backward at the microscopic scale. The universe's sheer complexity makes that reversal vanishingly improbable. Once entanglement has spread through trillions of particles, the correlations needed to reverse it would require a precision beyond imagination. It's as though the universe keeps a secret ledger of every interaction, and while nothing is truly lost, the information becomes so deeply buried that it might as well be. Some physicists suspect that this is where classical reality, the everyday world we inhabit, actually comes from. Not from measurement or consciousness, but from the thermodynamic consequences of decoherence. When enough quantum systems interact, the web of entanglement grows so vast that coherent superpositions collapse into practical irreversibility. Entropy doesn't just mark the arrow of time. It builds the solid classical world we experience within it. Our familiar universe, with its definite objects, memories, and histories, may be a kind of emergent illusion, a high entropy approximation of the deeper, time-symmetric quantum realm beneath. That's a sobering thought, that reality's solidity, the sense of this happened, not that, may be nothing more than entropy's shadow. The irreversible, the permanent, the real, all of it arising from the loss of possibility. And yet, there's something quietly poetic about that too. The same principle that dissolves information also creates meaning. The act of decoherence, of collapsing infinite potential into a single experience, is not so different from life itself, a narrowing of possibility into one improbable thread of being. Entropy, then, is not merely the price we pay for time's direction. It may be the very process through which the universe becomes aware of itself, through which the quantum fog condenses into the tangible world of stars, stones, and human thought. Quantum mechanics complicates the arrow of time because it reveals how fragile that arrow really is, how easily it could, in theory, point either way. But it also shows us that direction, and the meaning that comes with it, emerges naturally when complexity grows. The laws are reversible, life is not. At the smallest scales, time may be an illusion, but at the scale of human experience, the warmth of a memory, the sound of a heartbeat, the fading of a star, the illusion becomes indistinguishable from truth. And perhaps that's the secret the quantum world has been whispering all along, that the universe doesn't need time to exist. It only needs enough entropy to dream it. In 1948, a quiet revolution took place, not in physics, but in the mind of an electrical engineer named Claude Shannon. Shannon worked at Bell Labs, the birthplace of much of modern communication. His goal was pragmatic, to find a way to send messages efficiently through noisy telephone lines. But what he discovered reached far beyond telephones. It reached into the foundations of physics, mathematics, and the nature of reality itself. He showed that information, the abstract stuff of messages and meaning, could be measured, quantified. And the unit he used was the same word physicists already knew so well: entropy. Shannon's information theory defined information not by what a message says, but by how uncertain it is before it's received. A message that tells you something you already know carries no new information. A message that surprises you carries a lot. He derived a simple formula to describe that uncertainty, a mathematical cousin of Boltzmann's equation for thermodynamic entropy. The more unpredictable a system, the greater its information entropy. In physics, entropy measures the number of microscopic arrangements that could produce a given state. In information theory, it measures the number of possible messages that could emerge from a given source. Both describe ignorance, the missing knowledge that separates what could be from what is. This connection was more than coincidence. It hinted that information and entropy were two sides of the same coin. One measured uncertainty in matter, the other in meaning. And from that insight, a new picture of the universe began to emerge, one not made merely of particles and forces, but of bits. A bit, Shannon's basic unit of information, represents a choice between two equally likely alternatives: yes or no, 0 or 1, on or off. Every decision, every observation, every distinction that separates one possibility from another adds or removes a bit of entropy. The more uncertain a system, the more bits you need to describe it. And the more certain it becomes, the more you know about it, the lower its entropy. So while physicists once thought of the universe as a collection of matter and energy, Shannon's work suggested another layer beneath, the universe as a vast information processor. Every atom's position, every photon's spin, every quantum state carries bits of information. Every interaction, every measurement, every moment that passes transforms and redistributes those bits. To some thinkers, like John Archibald Wheeler, this wasn't just a metaphor. He famously proposed the phrase "it from bit," the idea that physical reality itself arises from the information it contains. Matter, energy, even space-time might be secondary, emergent properties of a deeper informational substrate. In that view, the universe doesn't contain information. It is information. But the most dramatic test of that idea came from one of the strangest objects in the cosmos, the black hole. When Stephen Hawking combined quantum mechanics with general relativity in the 1970s, he discovered something astonishing. Black holes aren't entirely black. They emit a faint glow of thermal radiation, now called Hawking radiation, as quantum particles near the event horizon flicker into existence and escape into space. Over immense timescales, that radiation causes black holes to lose mass and eventually evaporate. But that leads to a problem, the information paradox. If everything that falls into a black hole is lost forever, and the hole itself eventually disappears, then the information about what it once contained seems to vanish completely. And that violates one of the deepest principles in physics, that information, like energy, can never be destroyed, only transformed. Where does it go? Hawking's calculations suggested the radiation carries no trace of what fell in. It's pure thermal noise. But if that's true, the universe would lose information, and with it, its ability to obey its own laws. This paradox has haunted physics ever since. Some argue that the information is somehow encoded on the event horizon itself, a vast cosmic surface storing the details of everything that has ever crossed it. This idea led to the holographic principle, proposed by Gerard 't Hooft and Leonard Susskind, that the entire contents of a region of space can be represented by information inscribed on its boundary. In a sense, every black hole is a memory, a two-dimensional archive of the three-dimensional universe. Reality, at its most fundamental, might be a projection from such informational surfaces. It's an idea so strange it almost sounds poetic, that the universe writes itself on its own walls. Entropy and information intertwine here in their purest form. To increase entropy is to lose track of details, to blur distinctions. To gain information is to reverse that blur, to sharpen the picture. But both are limited by the same balance. The cost of knowing is heat. The cost of erasing is energy. Every act of learning, whether it's a photon interacting with an atom or a human reading a sentence, rearranges the flow of entropy and information. Each bit we gain must be paid for in energy. It's a quiet, universal economy. Every discovery, every computation, every thought burns a little fuel, and that means information has a kind of moral symmetry. It can't be created or destroyed freely. It must be earned. In this light, entropy becomes something richer than disorder. It is the measure of everything we don't know, the infinite backdrop against which knowing becomes meaningful. Ignorance and truth are bound together by entropy like shadow and light. Without ignorance, there would be no surprise, no discovery, no curiosity. Without entropy, there would be no information to learn, no difference to perceive, no universe to observe. Entropy is the poetry of uncertainty, the quiet pulse of ignorance turning into knowledge, and back again. Every photon, every thought, every whisper of reality is a note in that endless exchange. And perhaps that's the truest way to think of it. The universe doesn't hoard its secrets. It continually forgets them, and in the forgetting, we find our meaning. The story of life is the story of entropy learning to dance. At first glance, they seem like opposites. Entropy pulls everything toward disorder, while life builds cells, organs, and ecosystems, astonishing pockets of structure and precision. But look closer, and you'll find they are inseparable. Life is not a violation of the second law of thermodynamics. It's one of its most elegant expressions. Long before living things existed, the young Earth was a planet of chemistry. Oceans simmering with simple molecules, volcanic vents spewing energy into the sea, lightning igniting the sky. In that chaos, gradients of heat and chemistry emerged, hot against cold, acidic against alkaline, light against dark. Wherever there was contrast, there was potential, a slope down which energy could flow. And from that flow, order began to appear. In the 1950s, chemists Stanley Miller and Harold Urey tried to recreate the early Earth in a glass flask, a mix of gases like methane, ammonia, water vapor, and hydrogen, shocked by electric sparks meant to mimic lightning. Within a week, the water had turned brown, and inside it formed amino acids, the building blocks of life. It was a revelation. Complex molecules could emerge naturally from simple ones, given energy and imbalance. Entropy wasn't being defeated, it was being channeled. Over countless millions of years, molecular networks learned to capture and reuse that flow of energy. Eventually, self-replicating systems appeared, precursors to RNA and DNA, molecules capable of storing information and making copies of themselves. Each step toward life was a local reduction of entropy, but only because it produced a greater increase elsewhere. The molecules that built protocells radiated heat into the water around them. The chemistry that stored energy as bonds released more energy as waste. Life didn't halt the second law. It accelerated it. To understand how, it helps to look upward. The sun, blazing at nearly 6,000 degrees Celsius, about 10,000 degrees Fahrenheit, floods Earth with low entropy energy in the form of visible light. The planet absorbs that energy and re-emits it as infrared radiation, higher entropy heat, at a much lower temperature. That difference between the sun's concentrated light and the Earth's diffuse glow is what makes life possible. Every organism on the planet depends on that flow. Plants use sunlight to build sugar, animals eat plants, and everything eventually decays, returning energy to the environment in the form of heat. The sun, in this sense, is an entropy engine. It drives the Earth's weather, geology, and biology by pouring in low entropy energy that life uses to create temporary order. A sunflower turning toward the light, a bird taking flight, a human composing a song. All are fleeting shapes carved from the sun's entropy gradient. The evolution of complexity, too, follows the same thermodynamic logic. Complex organisms aren't accidents that defy entropy. They are highly efficient mechanisms for dissipating it. When energy flows through a system, the system tends to organize itself in ways that enhance that flow, a principle known as dissipative adaptation. In rivers, it creates meandering channels. In weather, it produces cyclones. In biology, it gives rise to metabolism and evolution. The biophysicist Jeremy England has argued that life may be an inevitable outcome of thermodynamics. Under the right conditions, matter naturally self-organizes into forms that maximize energy dissipation. In that sense, evolution is entropy's way of improving its own efficiency, a cosmic feedback loop of creativity. Each organism, from bacteria to humans, is a temporary structure that captures energy, uses it to maintain order, and releases even more energy back into the environment. The more complex the structure, the more ways it finds to accelerate entropy's spread. That's what evolution does. It refines the art of imbalance. If entropy is the measure of the universe's drift toward equilibrium, then life is the local resistance to that drift, the brief whirlpool in the river's flow. We arise, consume, reproduce, and eventually decay, all while helping the universe relax toward stillness. It's humbling to think that our most sophisticated acts, thought, love, curiosity, are thermodynamic side effects, the glow of order burning through its own impermanence. But it's also beautiful. Because without entropy, there would be no time, no change, no life. We are not exceptions to the second law. We are its finest expression, living eddies in the current of entropy, swirling for a while before dissolving back into the vast, quiet equilibrium from which we came. And maybe that's the true meaning of time's arrow. Not a path from life to death, but a continuous transformation. The universe breathing, creating temporary order to better let go of it. Imagine time not as a straight arrow, but as a circle. No beginning, no end, only endless recurrence. The universe expands, decays, and perhaps one day begins again, not in memory, but in rhythm. In the late 19th century, the mathematician Henri Poincaré proposed a haunting idea known as the recurrence theorem. It states that, given enough time, every system of particles, no matter how chaotic, will eventually return arbitrarily close to its initial state. In other words, if the universe is finite and governed by deterministic laws, it could, in principle, repeat itself. The same stars, the same galaxies, perhaps even the same thoughts, might one day reappear, indistinguishable from before. It's an unsettling but strangely elegant vision. Eternity not as endless novelty, but as the recycling of the familiar. In practice, the timescales involved are almost incomprehensible. The number of possible states of the universe is so vast that the recurrence time would exceed any duration we can meaningfully conceive. Still, the concept resonates. It suggests that entropy's rise, though relentless, might not be the final word. Given infinite time, even disorder might fold back upon itself, allowing order to re-emerge from its own ashes. Modern cosmology has found ways to echo this ancient intuition. The idea of a single linear universe born in one big bang and ending in a final heat death may be too simple. Some theories imagine cyclic cosmologies, universes that expand, cool, and then, through some hidden mechanism, contract or reset, giving birth to new cosmic epochs. In one version, entropy from the previous cycle seeds the conditions for the next, ensuring that each universe carries the faint imprint of its predecessor. Among these visions, few are as bold as Roger Penrose's conformal cyclic cosmology. Penrose imagines that when the universe reaches its ultimate stage, vast, empty, and cold, particles lose their mass, and with it, the meaning of time itself. Without scale, the distinctions between moments vanish, and the universe's cold infinity becomes mathematically equivalent to the hot, dense beginning of a new Big Bang. The end folds seamlessly into the beginning, like two edges of a circle touching. In his view, the bang that birthed our universe may be the quiet afterglow of a previous one. It's a dizzying thought that the birth of everything could emerge from the death of everything. The arrow of time, instead of being broken, loops upon itself, guided by the same mathematics that governs light and geometry. Even entropy, usually the symbol of finality, finds renewal here. If the cosmos continually resets, then no information is ever truly lost. It only transforms, dissolves, and reappears in new forms, like memory reborn in another life. The parallels with human imagination are hard to ignore. Ancient philosophies spoke of reincarnation, the soul reborn in different bodies, cycling through lives until enlightenment breaks the loop. Friedrich Nietzsche, in the 19th century, reimagined the idea as the eternal return, the possibility that every event in your life will happen again, infinitely, exactly the same. It was not a prophecy, but a challenge, to live in such a way that you would welcome the repetition. These echoes between cosmology and philosophy suggest that the human mind has always sought patterns in eternity. Whether in myth or in mathematics, the idea of recurrence offers a kind of comfort, that endings may not be absolute, that even decay might be part of a larger harmony. And yet, perhaps time doesn't need to loop or restart. Perhaps it never truly began and never truly ends. Our notions of beginning and ending may themselves be illusions born of limited perspective, artifacts of living creatures who experience existence in sequences rather than wholes. To the universe, there may be no first moment, no last one, only an unbroken fabric where every event simply is. If that's true, then time's arrow is a matter of perception, not of nature. We experience its flow because we exist within entropy's unfolding, bound to its forward rhythm. But beyond that, beyond the scales of galaxies and heat death, time may dissolve into something timeless, a realm where being and becoming are indistinguishable. Perhaps that is eternity, not endless duration, but the absence of duration altogether. A universe that has always existed and will always exist, pulsing through cycles of creation and dissolution, aware of itself through the brief miracle of consciousness. And maybe, in those rare moments when we feel the present stretch and blur, when the world seems still and time seems to pause, we catch a glimpse of that deeper truth. The eternal now, where nothing begins and nothing ends, and everything simply continues, forever becoming itself again. In the end, the story of entropy is not about destruction, but about balance, a quiet, patient unfolding of everything that is. It is the law that allows things to happen, the reason stars burn and hearts beat, the thread that connects creation to dissolution. Without it, there would be no motion, no change, no story to tell. Order and disorder are not enemies, but partners in the same cosmic dance, one building, the other dissolving, both necessary for the universe to breathe. When we think of entropy, we tend to imagine loss, the fading of light, the cooling of stars, the slipping away of moments we wish we could hold. But what if disorder isn't the villain of the story? What if it's the source of everything beautiful? The reason sunsets blaze, the reason music moves us, the reason life can exist at all. Perfect order would be unbearable, static, silent, dead. It's imperfection, imbalance, and transience that make the universe alive. Every moment of symmetry must eventually break. Every structure must someday crumble. Yet in that breaking, something new is born. The dust of dying stars becomes the soil for new worlds. The heat that leaves your body tonight might someday warm another corner of the cosmos. The universe wastes nothing. It simply changes form. Entropy reminds us that beauty is not in permanence, but in impermanence, in the fragile, fleeting structures that briefly resist the tide. The shimmer of a wave before it falls, the last breath of a melody before it fades into silence. These are not failures of eternity, but expressions of it. They are the ways the infinite finds shape for just a moment before letting go again. Maybe time's arrow isn't something that drives us forward, but something we gently ride. A current through the vast sea of being. We drift with it, through growth and decay, through order and chaos, carried not toward an end, but through endless transformation. And in that current, we find meaning not by resisting change, but by flowing with it, by seeing the beauty in each passing moment and the grace in its disappearance. So as this reflection comes to a close, take a breath, feel the quiet pulse of existence around you, the warmth of your own body, the whisper of the world still unfolding. These too are part of Entropy's song. Thank you for listening and for being part of this long, slow conversation between the universe and itself. If you found calm or wonder or a moment of thought here tonight, I'd love to know where you're listening from and what time it is there. And if you'd like to keep drifting through the mysteries of existence together, you're warmly invited to subscribe. Until next time, rest well. And let the universe carry you, softly, wherever its current flows.